Welcome to a wired-in tutorial for the Computational Humanities, Arts and Social Sciences Initiative through the Faculty of Computing and Data Sciences. Today we're hearing from Professor Neha Gondal. She's an Assistant Professor of Sociology within the College of Arts and Sciences and also within the Faculty of Computing and Data Sciences. Her primary research explores the relationship between social networks and the cultural production and maintenance of social inequalities. She uses cutting-edge statistical techniques in conjunction with social networks and agent-based models to study diverse contexts such as elite consolidation through money-lending ties in Renaissance Florence, inequalities in academic communities evident in citation and hiring networks, and the clustering of unhealthy outcomes in Boston's public housing developments. Network observations typically involve high interdependence, which violates independence assumptions of standard statistical models such as linear regression. In this tutorial, Dr. Gondal will introduce some statistical models that can be used to analyze high dependence network data. These include exponential random graph models, quadratic assignment program, and stochastic actor-oriented model techniques. Please join me in welcoming Professor Gondal.
Thanks, Wesley, for that introduction. So I'll probably only have time to touch upon ERGM and QAP in this tutorial. I'm happy to talk about other kinds of techniques. If you have questions, please feel free to reach out to me. So before I get started, so this is a tutorial in statistical models and social network analysis. So it makes sense for me to maybe say a little bit about what social networks are before we get into the statistical modeling of networks. So I know when I say the term networks, people generally think of LinkedIn and Twitter and Facebook and so on. There are some people here who in this audience who've taken my class in social networks, so they know that I don't generally study those kinds of platforms. But social networks refer to connections between entities, any kinds of entities, and howsoever we can think of measuring connections. So typically we can think of those entities as being individuals or organizations. So we can think of friendship relationships between individuals, for example, or interorganizational ties, which could be upstream, downstream kinds of production-related ties. It could be cooperative ties, ties of competition, and so on. So effectively, essentially, a social network is only limited by your imagination of what you can think you can represent as a social network, but it is composed of entities, individuals, organizations, and the connections between those entities. Now, the thing with social networks is that because these entities are connected to each other, they're not independent of each other, right? Because if A is friends with B and A is friends with C, then A and B and C's behaviors are going to be dependent on each other by virtue of interaction with each other. So the standard kinds of statistical techniques and models we are used to using for modeling, say, survey data, like linear regression, logistic regression, HLM, and so on, they don't work in this context. And I have a quote here from a paper going back almost 100 years now, a seminal paper on statistical techniques that can be used to analyze social networks. And Moreno and Jennings in this seminal paper say, owing to its specific characteristics, this new field demands a new appropriate treatment. It was evident from the start that existing statistical techniques could not be automatically transferred from other fields to this new field. The problem is therefore what kinds of statistical methods can be constructed for this new purpose. So this is a time where social networks as a kind of data and as a kind of theoretical approach to doing analysis was emerging. And Moreno and Jennings conducted this very simple analysis in the 1930s where and this is before high-end computing techniques were available, they literally picked names out of a hat over and over and over again. They measured a social network of relationships, who's connected to whom, of friendships. And then they compared how names picked out of a hat the distribution of those kinds of the structures made by networks constructed by picking names out of a hat compared to the empirical network they had. And then they tried to compare these two kinds of distributions. Effectively, what they had done was generated a rudimentary simulation by picking those names out of a hat. Now, we don't need to pick names out of a hat anymore. We have better technology or easier, faster technology to be able to run simulations for us. But just to reiterate before we get into the general framework of statistical models for social networks, is that network data are not IID. They're not independently distributed. Like I said, if A and B are organizations, and they have a cooperative relationship with each other, and A and C is another organization, and A and C have a similar relationship, then we cannot assume that their preferences, the way they do things, their revenue models, etc., are going to be independent of each other. On the other hand, they're going to be connected. Now, typically, we use clustering models to account for this kind of interdependence, such as hierarchical linear models, which account for interdependence of errors. But the problem with social network data is that it's hard to tell us where this interdependence stops. Right? So there are assumptions we can make about how far this interdependence extends. But in the case of HLM, for example, if we've got data on children in a classroom, we can assume that all the children within one classroom are going to behave somewhat similar. Their observations are interdependent, but then classrooms are nested within schools, so we can assume a nesting structure. That's harder with networks because we don't know where this interdependence stops, right? Does it extend to 2 ties, 3 ties, 4 ties over? In fact, we have research that suggests, for example, that contributions to presidential campaigns are similar between organizations, even up to 3, 4, 5, 6 links apart, right? So there is a lot of interdependence in network data. So this violates standard assumptions of independence that we might use in other kinds of statistical techniques. And so we need to come up with a different framework to model social network data, okay? And so generally speaking, I'm going to talk about QAP today, and I'm going to talk about ERGM today, exponential random graph models, and both of them work under similar principles. The general idea is that we have one observed empirical instance. Now, that's typical. You're going to collect data on maybe once, or perhaps you have 2 networks, but you're going to have, some empirical data. And our goal is to formulate a model that helps us explain patterns in this data. So far, I'm not seeing anything that's different from any other kind of statistical analysis you're doing. Your goal is to locate patterns, right? And the modeling environment, the statistical modeling environment in social networks assumes a fixed set of nodes. That's one of the main constraints we place so that if our data has 100 nodes, we're not going to be using networks that have 110 nodes or 120 or 150 nodes and so on. So we're going to place restrictions on the number of nodes. The second thing to keep in mind is that our variables in statistical modeling of social network data are not typically attributes of individuals. While we can account for those are not our typical variables. Our typical variables are ties between individuals, these connections between entities, right? What is the likelihood that a tie will be present? Or how likely is it that friendship and advice relations are interdependent on each other? So unlike modeling survey data where you're trying to predict, for example, what explains voting behavior, and you have a bunch of independent variables such as gender, race, age, geographic location, and so on, what we're trying to understand is the structure of the network, not individual preferences, opinions, and so on and so forth. Now, I'll say one thing. I'm not going to show you any equations. The goal of CHASS tutorials is to be generally accessible. So it's going to be a non-technical introduction. Many of the people here are CDS students. So for them, it might seem too non-technical, but the goal is to offer something that is accessible to more people. So that there are going to be no equations at all today that I'm going to show you, okay? Now, the other thing to keep in mind, and the reason we need to use simulation-based approaches, is like, unlike things like age and income and so on, we don't have distributions, existing distributions against which to measure the properties of our empirical network. For example, we don't have a set of distributions against which we can compare how many triads there are in my network, how many of the dyads are reciprocated, right? Unlike measuring, for example, is the difference between the mean of these two populations in income, is that statistically significantly different or not? We have statistical theory that guides us, right? In this case, we don't have existing distributions, and so we must generate our own distributions based on some restrictions that we place on the space of those distributions in order effectively to generate those distributions. So the idea is very simple. We don't have these distributions. We simulate our own networks based on certain kinds of restrictions and compare our empirical instance or structural properties of our empirical network to our simulated distribution. To the extent we have those distributions are close enough, right, within reason of statistical variation and process of stochasticity, we believe that we've generated a good distribution, right? On the other hand, if there is a vast difference between the structural features that are reproduced in our simulations and our empirical network, that gives us reason to believe that we have not specified our model accurately and we should go back to the drawing board. Again, this is not that different from running a regression analysis, right? We put in some independent variables, we get an R-square, we run the model. If our coefficients are statistically significant and we see an improvement in the model fit, we believe that our variables have some explanatory power. It's not that different from what I'm stating here, that if our simulations are good, they should be able to capture the structural properties of our empirical network. If they are not very good, then we need to redo those distributions by respecifying our model. That's the general framework, okay? Question? Yes?
Yeah, and when you say respecifying the model, do you mean like adding more parameters?
Yeah. Yes, absolutely. So I'll get to that in just a minute. Yes. So let's begin with quadratic assignment procedure. So typically, and this is sort of in the early quadratic assignment procedure was one of the first few statistical models that were developed in order to test statistical significance of within network data or using network data. Now, the typical case where quadratic assignment procedure makes sense is that we have two relations, two different kinds of relationships measured on the same sets of actors. So think of an organizational context, and you have friendship ties between people, and you could measure that by asking people, who are you friends with, who do you hang out with after work, whose homes have you been to for a meal, and so on. And then at the same time, you have formal organizational relationships based, let's say, on advice. So let's say this is a law firm. Who might you reach out to for advice about a case? So you have these two parallel kinds of relationships. And you believe that advice relations and friendship relations are likely to be interdependent, right? One idea could be that they layer over each other. Those from whom we take advice from our friends. That's one hypothesis. An alternative hypothesis might be that these two relationships are indeed orthogonal to each other. That is, advising is fundamentally a hierarchical kind of relationship, whereas friendship is an egalitarian kind of relationship, so the two of them don't go together, right? And you might be a consultant who's been hired by this organization to figure out why there is some degree of dysfunction in the organization. And you might be interested in figuring out if these two relationships are somehow in conflict And that could be one reason why people are not getting along. There's high turnover, there is low closure rate, and so on, right? So this is a typical problem that a consultant may be hired to deal with. And in addition to doing other kinds of analysis, you might also seek to gather network data and do this kind of analysis. Right? Now, we can't simply run a correlation analysis between friendship relations and advice relations because of interdependencies in the data. Right? That coefficient is not a valid measure of the relationship between these two data sets. Now, I'll say one more thing. Typically, for those of you who don't know how social network data are represented, network data are typically represented using matrices. What's a matrix? Matrix is an array of data where you might have, for example, if you're gathering data on friendships, you have individuals' names running along the top and the side, and each case is a 1 or a 0. Two people are friends, they're not friends, and so on. So instead of running a straightforward correlation analysis, what we're going to do is use a simulation-based technique called quadratic assignment procedure. And what that does, what we're simply doing, again, this is a non-technical introduction to statistical models. What we're doing here is first calculating the correlation coefficient between the two matrices. That can simply be done by rendering the matrices as vectors and calculate the correlation coefficient between the two vectors, right? The next thing we're going to do is hold one of our matrices constant and then permute the rows and columns of one of the other matrices hundreds and thousands of times without, and this is critical, disturbing the structure of the network. What you're doing effectively is you're doing row and column permutations so that you're not disturbing the structure and redoing the structure. Effectively, you're scrambling the names of, let's say, the friendship data. And by doing so, you're disturbing the relationship between the friendship and the advice matrix, right? And every time you you create a new matrix, you recalculate that correlation coefficient. And you do that hundreds and thousands of times. And by doing so, you generate a distribution of coefficients. And then the next step simply is to compare your empirical correlation coefficient to the distribution you've generated. If your empirical correlation coefficient is in the tails of the distribution, it suggests to us that that coefficient is not simply a random occurrence, but has statistical significance, right? So effectively, we have, rather than using an existing distribution against which to compare our coefficient, we've generated a distribution from scratch. Does that make sense? Okay. Now, this was a simple case of calculating a correlation coefficient, but QAP can also be used for more complex cases where you have, where you're interested in using social network matrices in regression analyses. Okay, so for any association between X and Z, this is straightforward statistics. There can be a number of other intervening variables, right? And we need to control for those variables. Again, we can't simply regress Y on X because we're back to the problem of interdependence. So we need to basically reproduce what I just said in this case in the framework of regression analysis. That is, we regress X on Z, we capture the residuals. We regress Y on Z, you capture the residuals, and you calculate the correlation between the residuals. And you do this over and over and over again, generate that distribution, but this time it's the correlation coefficient is between residuals. So again, a relatively straightforward process. Okay. So here's an example from research where QAP might be used. Let's say you're interested in understanding bill co-sponsorships between legislators. This is a very standard kind of problem in political science, international relations, and so on. It need not be bill co-sponsorship between legislators, but other kinds of networks that involve legislation, international legislation, and so on. And we might therefore have a data set that includes sponsorships between legislators. We might have a variable for whether or not the legislators belong to the same party, a variable about their ideologies, about their seniority, and so on. So we have the standard kind of data set, and there are lots of other techniques to do this, but the QAP version of doing this is to do exactly what I said in the previous slide, which is you have these two variables that you're interested in measuring. You run the regression, controlling for all sorts of variables. You calculate the coefficients over and over and over again so that you have a nice simulated distribution, and then you compare your coefficients against these simulated distributions. So QAP can therefore be used for other kinds of circumstances where you're using social network data in your regression analyses. Okay, I've got about 15 minutes left, so I want to switch to ERGMs, or exponential random graph models. Now, ERGMs are a different kind of statistical model, and ERGMs help us uncover the structural tendencies underlying the creation of a network. So you have a social network that you've gathered data on, and you're trying to figure out what are the principles that lead to the generation of this network. Okay? We can cast those principles both as social mechanisms as well as structural tendencies, right? So you're interested in figuring out whether this network is made up from stars and triads and reciprocated dyads and so on. So, you know, in that case, it's nice. A useful analogy I find is thinking of this as a Lego model, right? So you have a whole bunch of Lego pieces, different shapes, and you create a structure, right? And you're trying to figure out which structures are more prevalent, what kinds of microstructures are more prevalent and come together to generate the network as a whole. But these structures are substantively socially meaningful. For example, you might hypothesize or find inductively, as you do descriptive analysis, that there are a lot of star-shaped structures, which is that there is a popular node and a lot of other nodes connected to this. Now, typically in social networks, we call this preferential attachment. Now, preferential attachment results in the creation of star structures, but substantively, preferential attachment is a way of measuring inequality in popularity and inequality in resources, to the extent popularity is a resource. Depends on what you're measuring in the network. Okay? For example, in a high school network, we can think of popularity as literal popularity. You measured friendship relations or liking or admiring ties, and you find that some kids tend to be named very often and other kids tend not to be named at all. Standard story of most high school situations, and we find this repeatedly in high school data measuring friendship and admiring kinds of ties. And that is telling us that there is inequality in popularity, but the structural equivalent of that is that we find lots of star configurations, right? So the goal of ERGM is to figure out what are the underlying structural and social properties that give rise to this network. So there are a whole bunch of different kinds of parameters that can be included in ERGM. There's generally a distinction between what we call endogenous and exogenous parameters. Endogenous parameters are structural parameters made up only of structural bits in the network. For example, arcs, right? In a network where a tie originates from someone and ends at someone, such as money lending or admiring or advice, right? Versus siblinghood. If I'm somebody's sibling, they're my sibling. But if I give advice to someone, it's not necessarily that I seek out advice from them. So that's a directed tie. So endogenous variables are these structural kinds of parameters. And again, like I said, they have social meanings embedded in them. So reciprocity typically generates balance and exchange. Okay, so we expect certain kinds of relationships to be characterized by reciprocated ties and others not so much. So friendship, yes, should be characterized by reciprocated ties, but you'll be surprised at how many unreciprocated relationships we find in high school friendships. A lot of people say this person's my friend, but they don't report them back, right? Anything that's sort of hierarchical relationships, typically we won't expect much reciprocity there, okay? Stars, there are different kinds of stars. So I talked about just popularity coming in. There can be some people who say they have lots of friends and others who say they have fewer friends. So that's sort of an outgoing kind of star. Then there are mixed kinds of stars where individuals that receive a lot of ties and send ties, those that receive lots send little, and so on. So star configurations can also be of a variety of different kinds, okay? And then there can be different kinds of triads. Two very typical are what are called transitive structures and cyclical structures. Cyclical structures are little eddies. A lends money to B, B lends money to C, and C lends money to A. So that's sort of a cyclical structure. A transitive structure is one where A admires B, B admires C, and so A also admires C. Now these have different kinds of interpretations and different kinds of social logic that go into generating structures that have higher prevalence of transitive versus cyclical triads, and so on. Exogenous factors are ones where you can account for attributes, individual attributes. So for example, you might say that people who are older are more likely to send ties, or individuals who belong to a sports team. Kids who belong to sports teams in high school receive more ties than those who belong to the chess club. You can also account for things like homophily here, which is a very important principle in social networks. The idea that people tend to become friends or form relationships with others who are similar to them. This is a very important undergirding principle in social networks, and we find homophily to be prevalent in nearly any kind of network we find. A classic statistic, I haven't seen the most recent statistics, but generally from about 7 to 9 of our out of 10 ties tend to be race similar, for example, in the United States. So most of the people we name as being our friends tend to be of similar race to us. But homophily also applies to other kinds of things like educational qualifications, socioeconomic status, and so on. We can also use exogenous factors to measure multiplexity, so that the idea that if individuals that are more likely to lend money to each other if they are also friends with each other, right? So these are another example of exogenous kinds of parameters. So this is all to say that the microstructures that come together to yield the macro structure can be of a variety of different kinds, and we have a lot of choices in what kinds of parameters make sense. Of course, which ones you include and which ones you exclude are going to depend on the relationship you're measuring, on your theoretical instincts about what should have led to the construction of this network. You can't throw everything in. You're running a simulation, there are high interdependencies in the data, it's going to spit nothing out. You throw garbage in, it's going to throw garbage out. That reciprocity is statistically significant, having accounted for those kinds of triad structures. So is reciprocity a byproduct, or is it a fundamental generative mechanism of the network? That's what. Another thing it does is that it helps us figure out these different, possibly even competing mechanisms that could be leading to the generation of the network. For example, core periphery kinds of structures where there is this inequality in popularity may be generated either from starriness, this preferential attachment, or it could be the byproduct of a lot of triadic closure, right? And what ERGM does is it allows you put both of those structures in, it allows you to disentangle those structures by telling us which one is statistically significant and which one is not. So in this respect, it's not that dissimilar from other kinds of statistical techniques that you might use in the analysis of social science data. Most importantly, what ERGM does, one of the unique features of ERGM, is that it allows you to link micro and macro levels of analysis. This is one of those ideal goals in social sciences, trying to bridge these two different levels, and ERGM helps you do that, because fundamentally what ERGM is doing is using micro level structures and mechanisms to figure out what generated this macro level network. Now, we limit that precisely by specifying a model and saying we believe that this model should have reciprocity and it should have preferential attachment, but it's unlikely, given what I know about the context, given what I know about the type of relationship, etc., I don't think there should be much triangulation. I believe there should be homophily, I believe there should be multiplexity, but there shouldn't be these things. You specify the model, you run a bunch of simulations, and then you compare structural features of your observed network to your simulated networks. So there is no such thing as compare. You can compare visually the networks in your simulation. Let's say you ran 10,000 or 100,000 simulations. You pick 5 of those networks and compare those networks to your empirical network, right? But it's more informative to compare specific structural features, such as simply the number of arcs, the number of reciprocated dyads, the number of this kind of triangle, the number of stars, and so on and so forth. How many dyads are homophilous on each of the parameters of interest, right? And what the simulation does is that it generates a distribution for you, and it's very easy then to compare your empirical instance to the simulation and use standard, say, t-tests to see where your simulation lies on that. But unlike the t-tests, our goal here replicate, right? So some features are going to lie in the tails. The point is, if the most relevant features lie in the tails of the network, that suggests to us that that model is not a good model. Certainly, any of the features that are included in the model should be near almost at the center of the distribution. But anything that is not included in the model, but nevertheless is of importance to you, should also lie close to the center of the distribution. Okay, I can stop here. We're at 12:45, so I'll stop here. I'll take questions, and we can open the floor to discussion. Yes?
Can you talk more about using ERGMs to connect micro and macro level outcomes? Like, what would be a macro level outcome that you would see?
Sure. So let's say we're interested in figuring out if there is a lot of social closure in a network. So is this a space that's highly hierarchical and there is a lot of social closure? Now, we can think of social closure and measure that in a variety of different ways. One of those is there homophily in the network based on parameters such as social status, level of education, etc. Right? Let's go back to our law firm, our fictional law firm, where we're trying to figure out why there is high turnover, less productivity, and so on. So we might believe one of the reasons is that there is there's high level of social closure, but very little interaction across groups, right? So we want to figure out what is the basis of this kind of structure. Is it that people are mostly interacting with others that work in similar fields? Is it because people are mostly interacting with others that they are spatially close to, located close to, and so on. So this stuff that's happening at the micro level might in the aggregate come together. Tendencies, things that we don't think are that consequential, but when they aggregate up, they may create dysfunction by creating a lot of social closure at the aggregate level. Does that make sense?
So going off of like the same fictional law law firm example, because I mean I'm thinking like how do you collect this data, right? Because it's you can only collect so much like network social data, and so if your model that you like calculate is not very good, then how do you like re-specify it if you have very limited data to work with?
So the great thing about social network data is that even data on let's say the law firm has 100 partners and 100 associates, or even less, like 50 partners and 100 associates, right? That's a lot of data. That in itself is a lot of data. So if you've collected network data by creating a questionnaire where you ask people, can you tell us who in the past 6 months, who've you reached out to for advice on cases that you're dealing with at the firm? So, and or another way, and say, give me the top 5 names that come to your mind. Or another way of doing it is, here's a list of everybody who works. Can you check off all the people from whom you've taken advice in the last 6 months? And you do the same thing for friendship. Now, even that is a lot of network data. But I would say in the same survey, you also ask them for basic attributes, right? Like any attributes that you might not have access to from the firm's leadership. So the firm might make available to you general salaries, gender, race, ethnicity, and so on, these kinds of data. But any additional information that you think might be relevant, but that the organization may not provide to you. You collect those additional kinds of attribute data. And you don't need to go back and collect more data if your model fails. You need to think about what are the other ways in which the networks could be generated. Using your existing data, you re-specify the model. So especially with ERGMs, there's as much of an art to it as a science, and it requires a lot of contextual knowledge, right? So you have to be embedded there. You have to know the kinds of relationships that are more likely. Generally, we assume friendship is an egalitarian relation, but that may not be the case in this firm. It may very well be the case that friendship, or the people that people report having dinner with, tends to be superiors. They go to their homes for dinner because they're invited and they feel obligated. So if you're measuring friendship by asking people whose homes have you dined at, you might actually not be, your instrument might not be capturing friendship, it might be capturing hierarchical relationships. So you don't need to go back and collect more data, you just need to rerun the model using other kinds of measures based on perhaps a rethinking of the social factors underpinning the creation of the network.
Fascinating. Thank you, Professor Gondal. With this, strikes me that with ERGMs, there's a kind of optimization possibility available. So the way you presented it, we're making a theoretical guess about the network structure, and then we're testing to see whether the guess is any good. But that produces, that one guess could be competing with a lot of other guesses.
Yes.
So if you could parameterize the theoretical assumptions and map that parameter space across to the outcome variables after you've tested for closeness of fit, you'd be able to run optimization experiments to see which set of parameterized assumptions are best for that particular network. Isn't that correct?
Yes, although I will say that there is generally not a unique solution here. Many different models could provide a reasonably similar fit. I will, however, say that the parameter space is unlikely to be huge, right? If if you've captured the social factors and structural forces leading to the creation of a network, the 5 different models that provide a somewhat comparable fit are unlikely to be very different from each other, or in the aggregate are likely to lead to similar kinds of conclusions. So you could, like I said, capture core peripheryness using a preferential attachment model with triads, or just with a clustered triad approach, which may effectively amount to a similar kind of mechanism, right? But there is not a perfect model or the kind of optimization solution, to the best of my knowledge, that exists. You can, and the way to fit a good model is, yes, some of it can just be inductive. I have no idea, and let me try with a set of standard models. That's not a terrible way if you don't have familiarity with the context. But you're going to run a lot of descriptive analysis prior to running that model. If you don't do that descriptive analysis, if you don't have familiarity at all with the context, you're setting yourself up for failure, effectively, because you're running simulations. Know what models tend to generally go together. But once you've done it enough, you have a good sense of these clusters of features tend to go together. And these clusters of features are often seen in friendship networks. These clusters of features are often seen in an organizational framework. You start with those, as well as descriptive analysis, you're more likely to get to a successful model.
Follow up?
Yes.
The sociological expertise you just described, that takes you efficiently towards models that are likely to be good fits, for the real world thing you've got. That's impressive, means you've got to stay talking to experts and so on. But you could be putting that method in conversation with a rigorous optimization method that is basically blind to sociology. And then you wind up with your top 10 models that's completely blind to the social considerations. Wouldn't that be an interesting conversation to have back and forth?
Yes, it would, except I mean, perhaps this is because I am a sociologist. I will say that I think unless you are very good, that is, have expertise at running ERGMs, being able to run a successful model into the context is not likely going to lead to very successful models. And the reason is, first of all, in some sense, being completely blind to context means fitting only endogenous models, because the second you start including exogenous attributes, it implies social expertise or social scientific expertise, right? And entirely endogenous models are unlikely to be successful. Those that don't account for homophily, multiplexity, exposure, differential capacity to receive and sentize. Entirely endogenous models can be good, but they rarely are sufficient at providing good fits.
Yeah, to kind of follow up on what he said, so would it be possible to, like, let's say, use AI agents to embed the context as a prior and then test like multiple hypotheses? Because I mean, out of this whole process, I'm guessing the most manual part would be like respecification and rethinking like how you're structuring the model. So I'm just thinking, like, how do you combine it? Because I know you mentioned at the beginning you're working with agents. So is this like kind of AI agents, like LLMs, or what is that?
I don't know if LLMs have been used or AI has been used to run ERGMs. Basically, you're saying take the social scientist out of running the ERGMs. You know, the thing is, I'm sure you can create an AI model where you submit to it all the possible ERGMs that have been run and published in academic journals, and then that'll presumably train the AI in a way, in some kind of classification that it says this kind of network structure fits well with this kind of model. But that's the sort of social scientific expertise that I've built over 2 decades of running these models, right? So I think that sure, AI can possibly replace me.
My question is more like how can you utilize AI to like make this process even faster, and so that you can use your expertise instead of doing like really nitty-gritty tiny manual labor, like go more like high level.
So I would say that AI would probably help if I had a situation where I had many networks to model using ERGM, right? And so let's say I had data on 1,000 high school networks, and those kinds of data sets exist in the United States. I don't know how many the adolescent health or the ad health data set has, but it definitely has network data on adolescent sexual, romantic, and friendship ties from high schools and many waves of them. So in that kind of context, I know people who've basically manually model those without, and this because it was like 15, 20 years ago that they did this. But the AI part of it is that once you've run the model on like 5 of them, you have a good sense of the underlying structures, and so you're able to fit a same kind of model on other similar structures. So yes, I think certainly AI would be good to be able to train it to say, if you have to do the descriptive network analysis and say if these kinds of descriptive features, right, so number of triads, number of reciprocated dyads, relative number of, these different kinds of features, then test this kind of model. So certainly I think AI can do the bridge from descriptive to running the model. But again, I think AI would be probably good at doing basic kind of homophily, just because we find homophily in every network, and basic kinds of endogenous structures. But anything more complex than that, how the two of those intersect and how they should be more or less prevalent in a given context, you would need some human expertise for. But yeah, it's a good idea. I'm not a methodologist, but I'm certainly happy to talk to methodologists who do create ERGMs and ask them where they are on AI and ERGMs.
One of the things that came up for me was thinking about network changes. So if we're thinking about a high school situation, people can become friends and not be friends at a later time. But also in the law firm example, you can have people get promoted, right, to partner, and maybe that changes the relationships that they have. Do you have any recommendations on what kind of approach you would take to modeling like kind of dynamic networks or changes in networks over time? I think these look more like snapshots to me, but it'd be great to know a little bit more about that sort of, modeling a network over time.
Yeah, so ERGMs are snapshot approaches, and the dynamic equivalent of those are stochastic actor-oriented models, which are basically dynamic ERGMs but have certain assumptions in them, embedded in them, such as those of agency, who's doing the sending of ties. And one of the assumptions in stochastic actor-oriented models is that the sender of tie has agency. And certainly stochastic actor-oriented models are somewhat limited, just because the context can evolve so rapidly that it can account for minor changes, but major upheavals basically effectively becomes a difficult to connect the dots between time 1 and time 2 if there's a major upheaval. But if you have overtime data, then you certainly can also model not only the structure of the network, but how the network is evolving over time using stochastic actor-oriented models.